Okay, I'm gonna quickly reiterate what we did in the MDE course, because we had some really good examples. Okay. Now, first thing is an application of rational functions. We have, let's say these are fish reproducing rather quickly, small fish. We have unstriped fish and striped fish. Okay. The number of unstriped fish changes with time. We're raising these things, we're selling, okay? And the number of unstriped is 16T plus 90. So meaning if T is 0 right now, we have 90 unstriped fish. Striped fish is 14T plus 80. And so if T is 0, we have 80. So we have about the same number. If we look at a sample of the fish, look at them and say, they're pretty close to the same, and that's kind of what we want. Okay, we want to test to see whether it is going to tend to stay the same if this model continues. So we want to look at the ratio of striped to unstriped. Right now, the ratio is 80 to 90, or 80 over 90. Okay, and that's pretty close to 1. 80 over 90 is like 0.88. But more. Okay, so anyhow, there's your ratio, striped to unstriped. Now, in general, the ratio is going to be the number of striped over the number of unstriped, which is 14T plus 80 over 16T plus 90. Well, to get a visual of how that ratio is going to evolve, we're going to graph R of T versus T. So here's your R, here's your T. How do you graph a rational function? Oh, you first find intercepts. Okay. So if T is 0, you're going to get just plain old 80 over 90. That's the ratio we have now. Okay. So I'm going to say that that ratio is about 0.9. Okay. Then get the x-intercept. Oh, you set the thing equal to 0. Well, you're going to set this equal to 0, meaning you're going to multiply both sides of the equation by the denominator, which multiplied by 0 goes away. Now you also want to keep in mind that the T can't be negative 90 over 16. Okay? Because then you'd be multiplying both sides by 0. It turns out that negative 90 over 16 is going to be vertical asymptote of the function, because that means the denominator 0. The numerator is. Now, those are all things we need to know about that function. So I'm saying this rather quickly. So what we get, and I'm not sure I've got the numbers right here. But I went systematically, intercept, vertical intercept is T equals 0. We get 80 over 90, 8 over 9, that's about 0.9. Okay. And these approximations, turns out these numbers, some of these numbers are very close to others. So you can work out your own numbers. I'm not even going to claim that the graph is totally accurate. Okay. Horizontal intercept occurs when R of T equals 0. Then we set this ratio equal to 0. Multiply both sides and all that. Here we get T is about negative 5.7. So we can put those 2 points on the graph. Get the intercepts. Then we look at the long run behavior. Well, in the long run, R of T approaches 14 over 16. Okay. And that's like 0.885. And it is a little less than what we get here, which is really like 0.889, but not much less. In other words, the Y value of the intercept is a little bit higher than the Y value of the asymptote. Okay. This is going to be a horizontal asymptote because that's what you get if you push it infinity negative. And that's easy to work out this function. It's easy to verify what I just said. Relatively easy. You just got to know to do it. Okay. And then you have vertical asymptotes. Well, there's only one, but you write the plural just in case you come up with more than one. It's pretty obvious that you're going to want to be one value of T that makes the denominator 0. And at that value, the numerator won't be zero. Although the numerator is close to zero. Okay, so we do that, we get t approximately negative 0.56. And at this point, I was fudging a little bit. That's what it's going. Okay, so anyhow, okay, well, that gets me a little too much to put on the graph here. So we put a graph on. So there's a vertical asymptote at this, then I rounded this to negative 0.57, which was completely accurate. Still, I think if you work out the numbers, I can see that, I don't want to discuss it. You work out the numbers accurately. This number isn't quite right. This number isn't quite right. It's not 0.56, it's 0.6. This zero is going to be a little bit to the right of this vertical asymptote, but again, they're going to be very close. You're going to get something that looks like this. Okay, you're approaching your horizontal asymptote on this side. You're approaching your vertical and horizontal asymptote on this side. You're approaching the asymptote through positive values on this side, through negative values on this side, and that's a good thing. That's the only way we're going to get that graph to work. Okay, so you get something that looks like this. But still, this that when t equals 0 on, R isn't going to change much at all. The ratio is going to stay very close to what it was at t equals 0. Now, t equals 0 wasn't the beginning of time. It wasn't the time of the Big Bang. It was the time we chose to start looking at these things. Okay, and we probably bought the fish sometime before this particular instant, which means that some negative values of t are going to be relevant. Okay, we're going to know what we had when we bought the fish. Well, when did we buy the fish? Or when did we decide to populate this particular population? Okay, so that might have been at t equals -4. Okay. Could have been something else. It isn't going to be to the left of t equals -5.6 because the model totally breaks down at this asymptote. So everything changes as we cross this asymptote, and this part of the curve doesn't tell us a thing about our future. This part does, back to the point where we have the original mix. We can't go too far because the ratio can't go negative. We have to have a negative number of striped fish or a negative number of unstriped fish to get a negative ratio. One of these would have to be negative. Okay, so the domain of this model can't go past this point. And really can't be at this point, because at this point, we would have no unstriped fish. Well, that would actually be possible. We could have some striped fish at this point, and then they start reproducing and producing unstriped and striped fish. Okay, well, it gets complicated to reason this out. But you see that, you're probably not, if you're in business, and a number of people in this class, and a typical free calculus class are in business. I know it's not first period, looking at business. Kind of thinking you might not be in the fish business, but the ability to interpret a model would be very advantageous if you're in a business. Okay, you're trying to run a business. So it's an interesting model. With this model, we might say that, okay, this is a model, but Our domain. Not include times when, well, times that are irrelevant. Times before we purchase the fish, or times when the model just starts giving us certain results. Okay, well, there's that. $20 purchase depreciating 9% per year. These are just questions people came up with related to the sample problems I distributed last time. Okay. A $20 purchase depreciated 9% per year. If you're up on compound interest, this is just like compound interest, maybe compounding a 9% loss every year. And so after a year, you've lost 9%, you now have $18.20. Well, this thing's worth $18.20. Then you take 9% of that away and you get $16.40. Okay. You want to relate to the idea of compound interest, but now you're losing instead of gaining. If it was an investment at 9%, your model would be VFT equals $20 times 1 plus 0.09. Depreciating, so it's $20 times 1 minus 0.09. Here's your model. This A model is also a continuous model. And they're similar in the way they're solved. Anyhow, question then on the problem set. If you read the problem set, you've seen the question. After 26 years, what's the value of this thing? Well, you just plug in 26. The value is V of 26. V of 26 is what you get when you replace T with 26. And I estimate, just using rule of 72, that it's a little more than 3 half lives. So it's going to cut in half 3 times. It's going to be worth $10 after one of those, $5 after another, $2.50 after the third. So it's going to be in the neighborhood of $2.50. And I haven't really thought through how accurate the rule of 72 is, or particularly accurate rule of 70. So I'd say in the $2 to $3 range, if you work this out. Okay. Now, when is the value $7? Well, value $7. The value of $7 and VFT equals 7, because VFT is the value. That's an equation. You can write out instead of just writing VFT, write out what VFT is equal to, and you get a simple exponential equation you can easily solve. Okay. So what do we do to solve this equation? It should be obvious. We divide both sides by 20, since that'll go a long ways toward simplifying this. And at the same time, we can subtract the 0.09 from 1, we get 0.91 T equals 7 over 20. Well, that's in the form of B to the A equals C. We change that to the exponential form, the logarithmic form. Log base B of C equals A. H of T, so you get T equals log base 91 to 7/20. So we use then the fact that the log base 91 is the log of the number divided by the log of 0.91 and punch it in your calculator. And I think I estimated that it did $7. I was estimating 12 or 13 years. Okay. And it turns out that we can actually approximate this one pretty well. It's something between 11 and 12, I think. All right. Well, let's see. Then we do the continuous model. Continuous model is just our growth rate is negative 0.09. Now, our continuous model is the form A e to the negative R2, or R is the growth rate. Negative e to the point, A e to the negative 0.09 T. So there's our continuous model. It's going to give us a result pretty close to this one, but it's going to decrease a little faster. So we say that VFT is going to be set when, okay, we're not going to bother to find the, I didn't bother to write down the solution after 26, just plug in 26, punch in your calculator, you got that answer. then V of t equals 7. The solution is just a little different in nature. With one little twist that's different from this that we wanted to illustrate. V of t is 7. That means that 20 e to the negative 0.09 t is 7. We solve that equation. In the usual manner, we change to logarithmic form. We get 0.09 t, negative 0.09 t equals log base e of 7/20. Okay. And it turns out that 7/20 is 0.35, which is about the ratio you get after one time constant of the exponential function. So you're doing pretty good estimate. Then you don't need to know what I just said, but that estimate we believe it's around -5. So we have this. So negative 0.09 t. Now I changed log base e to ln because you don't know what e is. And log base e is a natural log, and you got to for that on the calculator. And even if you do know what e is, it's a pain to punch it in. Natural log is 7/20, and we divide that by negative 0.09, and we get the answer. Okay. So there it is. And again, I'm going to guess these should be maybe 11 point. Or even function calculators. It's always a question. Okay. What's the movie? Numerical approximation. I get them. Okay. Now, after that, we did some problems that could be disposed of pretty quickly. Okay. Simplify this expression. Well, that's very straightforward. I'm not even going to really discuss it much. The log of this times this divided by this is the log of this plus the log of this minus the log of that. Again, with practice, everybody comes into class doing this after they've done the homework. Okay, nobody has any trouble with it. But 2 weeks later, that's questionable, so make sure you review. And then we use the other rule that says log of x squared is 2 log of x, log of y to the 5th is 5 log y, log of z to the 7th is 7 log z, not log 7. Okay. Okay. Now, exponential equation, well, we just saw an exponential equation, saw a couple that are harder than this, and we solve them. There are 2 ways to look at this. One, you might recognize that 16 is a square of 4. Right? 16 equals 4 squared. And 16 equals 4 to the 16x plus 2. So 16x plus 2 must equal 2. Well, we're going to get that anyway, so we'll go through the process. So if you see that, that's a perfectly valid way to solve it. It's insightful. In the real world, it never happens. But we try to cut the solution a little bit. We translate this equation to logarithmic form. Here we got it. And then log base 4 of 16 is 2. Because 4 squared is 16. Again, that's something you do in your head. Probably want to punch it in to the calculator to make sure. Okay, you get 2 equals 16x plus 2, so x equals 0. And of course, assume we can solve that equation. There's another problem that I almost didn't do, but it's a little bit interesting. Log base 4 of x to the 6 equals 64. Now, and I hesitate with this. Is that really what I meant? Okay, is a log that's equal to 64. That's a pretty big number for a log. Means that x to the 6 is going to be a pretty big number. Okay. It's going to be actually unimaginably huge number. Because you'd be talking about 4 to the 64th when you convert this. What's 4 to the 64th? The 4 to the 5th is about 1,000. Okay. And 4 to the 64th is 1,000 raised to about the 11th power, which is going to have 30-some zeros. 30-some digits after the initial digit. So that's going to be a huge number. that you don't even want to bother to cheat. Some calculators couldn't even do it because it's going to exceed 10 to the 37th. That's as high as calculators used to go. Well, they probably go higher than that now. I don't use them. So. Okay. We translate this to exponential form and we get 4 to the 64th equals x to the 6th. Calculator probably might not even do 4 to the 64th, but we don't want to stop here. We want to take the 1/6 power of both sides so we get x. We solve for x, then we punch it into the calculator. But we don't even do that. It's 4 to the 64th to the 1/6. And we don't want to push the calculator to big numbers like that. It might crash on it. We do 4 to the 64/6, which could reduce to the 32/3. Okay. One way or another, we get that into the calculator. And I think we're going to get something around 3 million. We're going to take that instrument back. Another way to solve this problem, the reason I went to, the main reason I went to it is you can actually use the rules for logarithms and say that, well, log base 4 of x to the 6 is 6 times log base 4 of x. Okay. So that log base 4 of x is 64 over 6. And x is 4 to the 64 over 6. So you get to this without even having to worry about whether your calculator can handle 4 to the 64th. I say probably can, but that's one guarantee. It might still have restriction. Now we went back to the binary. That I don't totally, yeah. I don't have the code for how that was written, and I'm not sure I'd be able to read it if I did. So much for that. Okay. No, what the chip is on. That's what it okay. Another problem. Simultaneous equations. We start by graphing, and you get the intercepts. Intercepts of the first equation are 0, 5 halves, and -5/3, 0. Okay. Second equation, intercepts are 0, -10 over -4, -10, 6, 0. Well, we simplify those fractions and get 0, 5 halves, -5/3, 0. Well, let's say we plotted these. Now we're ready to plot these, and they land right on top of these because they're the same intercept. What does that tell us? It tells us that every point on this line gives us a set of x and y values that solve both equations. There are infinitely many solutions. We haven't talked a lot about that in class. You've seen it in the homework, you've seen it in the text. But we want to kind of address it, review it a little bit here. Okay, so there's our logic. These things have the same intercepts. Every point on the line is therefore a solution. Now, how does that look if we do Gaussian elimination? Well, we do our augmented matrix and reduce it, and this is what we're going to end up with. We're going to end up with a row of zeros. Now, this means that x minus 2/3 y equals -5/3. That's a perfectly good equation. This stands for the equation 0 equals 0. That's an equally good equation. It's always true, right? Doesn't interfere with the fact that this equation has to be true. So this equation itself is our solution. And we can pick any value for x and solve for y, or we can pick any value for y and solve for x, and we get an order pair that satisfies the equation. And we can do that with any value of x or any value of y, so there are infinitely many solutions. Now, if we change the equation slightly, and let's see if I got everything on. Okay. Here's the same left-hand side. First equation is the same as before, but the second equation got -20 instead of -10. Okay, Well, let's do a graphical solution. Graphical solution. Here are the intercepts of the first equation. The intercepts of the second equation are no longer the same as in the first equation. We've got a different number. The intercepts of the second equation are -10 thirds 0 and 0.5. Okay. Now, I've got a graph that looks like this. It turns out, in fact, that these lines are parallel, but they don't really look parallel when I do the graph. But still, it's going to be a ways out there before these lines intersect. Okay. And at that point, we might use a little common sense and say, okay, let's calculate the slope of this line and the slope of this line. Uh-oh, the slopes are the same, but they go through different points. Means they're parallel, means they never meet, means there's no solution. Now, maybe we do that, maybe we don't. That would be a good thing to do at this point. Of course, then we can go to Gaussian elimination. Gaussian elimination gives us this. Okay, now, there's a problem with this. The first equation is the same as it was over here. It's going to be x minus 2/3 y equals -5/3. The second equation is 0 equals -10. 0 equals -10? No, it's a different number. So this is a false statement. And if we get a false statement out of this, that means there's no solution. And that is what occurs if your lines are in fact parallel. Okay. Now again, if you hand sketch a pair of lines, or even sketch it on a good grid with a straight edge, you can't tell for sure whether it's parallel. Okay. Yeah, I did a fairly good graph here, but here's 5/2 unit. And here should be 5/2 unit, but this one was a little low. I knew it was a little low, but I didn't go off into my equation. Okay. Okay. This distance should be the same as this, and this thing is too far. Let's put this a little too far to the left. Well, that's easy to do. Okay. No big penalty. But when you hand sketch these, you can't always tell if the graphs are parallel. Also, the closer they are to parallel, the harder it is to get an accurate estimate for the graph. Well, here, no solution means the lines really were parallel. And that's true no matter whether the graph looked that way or not. And at this point, if you didn't already do it, you would probably be justified in that it would be a very good idea to calculate your slopes, see that they are equal, so that the lines can't possibly intersect. Okay, now I think that's everything we did. Those are good examples. And even for people in the support course, we just went over them in less than 30 minutes, where we spent almost 3 times that much going over them in that class. So if you want to see more detailed explanations, slower explanations, I'm posting support course as well as the pre-calculus course. So let's go on and look at some more examples. Okay. Let's take a system 3 equation and see how we might solve. Strategy. Yeah. So we pick a variable to eliminate. So let's first pick a variable to eliminate. Okay, I've got a 2x and a 4x here, so it'd be pretty easy to eliminate x between these two equations. Okay, now eliminating it between this equation and one of these might be a little hard, but it turns out that there isn't another variable that makes it easy. We might as well just choose x. Now, why? Well, why would be easy to eliminate from these two equations? You just double this one and add to this one, and we calculate since y and y. But this one and either of these would be Okay. Z, I have the same situation. You have 4 times this, would take care of that, but you got a 9 here, and so no matter which one we turn, we're gonna have to deal with some fractions. Okay. So we're just gonna bite the bullet and do that. Now, what we need to do is we need to eliminate whichever variable we choose. Between 2 pairs of equations, okay? Yeah, between like this equation, this one, and this one, and this one. That'll give us 2 equations, and the remaining 2 we can then solve this using the method of solving 2 systems, 2 equations. Okay. I'm going to choose, just so I can demonstrate that we can change the order of the equations. I'm going to choose to eliminate y. It's going to be to eliminate y between these 2 equations. And I'm going to write the equations in this form. You don't have to do what I'm doing. It does make things a little bit interesting. Now, I'm going to let this third equation be the equation 1. Now, there are 2 advantages to that. Oh, wait a minute, I think do that. Oh, yes, I can. Okay. One advantage is, one of the first things I'm going to do is I'm going to get a 1 in front of x. This equation, I'm going to do that by dividing by 3. On both sides by 3, and it comes out even. So I get nice even numbers. Okay. Again, I don't have to do that with the third advantages of that. Right. Then the second equation is going to be the other equation that I'm going to use to eliminate y. At least my first step. And then the third equation, I'm going to write down what was my first equation. So reorder. Now, I'll write the system one more time. Change what I number these. And they're just to be consistent. Remember, the number I put here is always the number of the equation I have in the previous step. So this was equation 3. This was always equation 2, and this was equation 1. So this is equation 3, and here this is equation 2, and 2. Okay. Now I divide equation 1 by 3. Equation 1 is not this equation, it's this equation, because it's the first equation in the previous step. Square, or then it's least several, least confusing in several potentially confusing ways. Okay, well, we divide this by 3, we get x plus 2, y minus 3 is 0. Then equations 2, 3. There's no advantage to multiply or divide any of these equations. Any number this way. Now, it's going to be relatively easy to eliminate y. Oh, no. Trying to eliminate y. what I did in dividing the first equation by 3. I could have done that, wouldn't have changed any of the solutions, could have gone on. It's come out a little easier if I divide the first equation by 6. Okay. Now, we're going to want to add 3 times the first equation to the second. When I do that, I get 3 halves x added to 4x. 3 halves x added to 8 halves x, which is 11 halves x. And then I have 3 times negative 9 halves c, that's negative 27 halves. Added to 4 halves is minus 23 halves. And of course, the numbers on the right are going to be easy if I happen to have a 0. Okay. Now I've eliminated y, and of course, 3 times y and minus 3y gives me 0y. So y. Then I'm going to want to subtract or multiply the first equation by negative 5 and add it to the third. And well, negative 5 times 1/2 is negative 5 halves. Add that to 2, which is 4 halves. So I think I'm going to get negative 1/2. Negative 5 times y plus 5 times y is 0. That's my goal. Get rid of y. And then negative 5 times negative 9 halves is 45 halves. I add that negative 8 z, which is 16 halves. Negative 45 and 16 is 29. Yeah. And that equals 1. Now, if I done that correctly, I want to take a second to check it out. I've got a system of 2 equations. It's not going to be difficult to solve for x and y. If we're just back, we're down to 2 equations and 2 unknowns. And we're not going to have any serious problem doing that if we have matched focus on 2 equations and 2 unknowns. Okay, let me check my numbers. Negative 5, that's 45 halves. Here's 22 and a half. Forty-five, 8. Okay, 14 and a half. Okay, that's good. Okay, now we solve this system. So we write this on. Yes. That is 43 half c equals negative 3 and negative 1/2 x plus 29 half z equals 1. Okay, now I observed it's gonna be easier to solve these, to get rid of the denominators. I always recommend on through by common denominators. Common denominators two in both cases. So we're gonna get 11x minus 23z, which is -6, and negative x plus 29z equals 1. Now this isn't working out, so I did something wrong, but you understand. It's lower the steps. I'm gonna wanna add 11 times this equation to eliminate x. That's gonna give me 111z here and here, and that's not right at all. So I'm just gonna take a second and see if I can catch my arithmetic error. But I'll observe that if I divide -9z by 6, I don't get -9 halves, I get -9/6, which is -3 halves. Okay. So that -9 halves has to become -3 halves. I'm going to back some of the numbers that I get subsequently. So I'm going to turn the camera off and make those corrections real quickly. Okay, let's go with that. Now, what I did again, I had -9 halves z, but -9 divided by 6 is -3 halves. Okay. And I just got used to writing the half there and just wrote that down. Yeah. Okay, now if I do that, then it corrects some of these numbers here. And I corrected everything. I also had a 1 here, when this should have been a 2, because I'm all published equation by 2. But again, I get these equations right. Then I write them down again. And I multiply each one by 2 in order to eliminate all the fractions, and now things come out really easily. If I add what do you want to eliminate? X, I'm going to eliminate x. So I'm going to add equation 1 to 11 times equation 2. That's going to give me no x. 11 times negative z, -11z, and that's -5z is -16z. And then 11 times 2 is 22 minus 6 is 16. We get z equals -1. Then I plug this into either of these two equations, because dealing with my simultaneous equations. Well, I plug z equals -1 into this equation. That gives me 11 halves x minus 5 halves times -1 is 3. So that'll be 11x plus 5 equals -6. 11x equals -11, x equals -1. Then I made the problems up. Just to give myself something that I could be pretty well confident in. I already knew that my solution is going to be -1, -1, -1. So we confirm that. Okay, then I can take x equals 1 and z equals 1 and plug them into any of the original equations. And really, I can plug this in for z. This in for x. And that gives me equation two times -1, 5y, and 8 times -1 equals 1. So that's -2, and this is +8. So that's 5y plus 6 equals 1. One more simple step, subtract 6 from both sides. Oh, divide by 5, you get y equals -1. So now all three variables are equal to -1. We can easily plug those into the other two equations and verify that they're true. Now, when I started this whole process, I didn't have to do this and I didn't have to do this. It just made things simpler. I could just start here and pick the first and second equation to eliminate x, first and third equation to eliminate x. Eliminated x, okay? Or I could have done that same thing with y and z. Pick these two equations, pick these two equations. Or pick these two, these two. And any of the three possible pairs of equations. And eliminate any variable. But we eliminate the same variable from both pairs. I chose to eliminate y to demonstrate a couple of possible techniques. If we had chosen, for example, to eliminate x from these two equations, I'd taken -2 times this equation plus this equation. That would have eliminated x. It's no different than it is for a system of two equations. It's just that when you eliminate a variable with three equations, you're still going to end up with two variables. That's why you got to do it twice to get two equations and two variables that you can solve. Okay, so I could have then eliminated x here. I have fractions, but we're going to get fractions no matter what we do. So I take -3/2 of this and add to this. That's going to eliminate x. Gives me an equation, two equations in y and z that I can solve. Not really, it's really no more difficult in solving a system with two equations. It's just that you have to know to pick a variable, eliminate it from two pairs of equations, then you're going to get two equations. And then you can use your back substitution and everything works out. Another real good question. We want to graph this equation. Okay, well, this is the transformation of log-base 2 function. We do -3 log-base 2 events. That's a vertical stretch. After -3. Or if you wish, a vertical stretch of 3 and a reflection across the x-axis. Maybe who's going to confuse the issue or not. I think I'm gonna do. Maybe make this whole thing. Okay, so let's say that, um. The G of X is belong to X to the X. Then. H of X. We can use any letters we want, but I want to name these functions, okay? H of X will be -3 G of X. And of course, that means we'd have a -3 log base 2 of X. Right? Now, we're building up the whole thing by transformation. So I'm going to let K of X equal H of X plus 4. Well, H of X is -3 log base 2 of X. So H of X plus 4 will replace X by X plus 4. M of X K of X minus 4. Well, K of X is 3 log base 2 of X plus 4. We got minus 4. Let me just say then that H of X we vertically stretch G of X by a factor of 3 reflected on the X axis, because that's what happens if we multiply a function by -3. All the Y values become 3 times as great and they change sign. The K of X X gets replaced by X plus 4. X in the H of X gets replaced by X plus 4. Vertical shift. -4. Then M of X will subtract 4 from the Y value of K of X, giving us a vertical shift of -4. So what's this look like? We do ground, log. If I was going to vertically stretch this in the positive direction, I wouldn't want my graph point to be too high. Because I'd run out of room at the top of the board. Anticipating that the first thing I'm going to do is vertically stretch the log base 2 function by a factor of 3 and put it on the opposite side of the axis. I'm going to leave myself a bit room down here. And I realize I'm going to have to go down to -6. Now, why? Because I understand the graph of the log base 2 function well enough to know my maximum y value of the basic function, function is going to be 2. So when I multiply by -3, I'm going to get a -6. And the graph is going to end up being down here. It's also going to be shifted. So it's actually going to be shifted. And that's going to end up pretty close to the bottom of the board. Okay. So here's my toolkit. Log function. Portrait of GeoDeck. And that's how log base 2 effects. And the collection. That's where we get the graph. Okay. First thing I want to do now is I'm going to graph the h of x function, -3 log base 2 function, because that's the vertical stretch, and we want to start with vertical stretches, and if there's a horizontal compression, we got to do those too before we start doing any shifts. The reason is very close to the reason why we multiply, why the order of operations, multiplication and division come before addition and subtraction. This is a multiplication. We do that before additions and subtractions. Okay. Well, the way I've structured these things in class. What do you do that, Earl? I am going to run into trouble up here. You can see what I mean, those are our arrows for the y values. Those arrows represent the y values of the log base 2 of x, and x equals 2, 4, 1.5, 4. I've got to reverse those arrows and triple their length to get the graph of my -3 log base 2 function. So I can reverse this one and simplify. This point straight for this because its value, the y value is 0, so 3 times the y value is still 0. Okay. -3 times this y value, well, there's the arrow for the y value of x equals 2. And that's going to give us a point about here. And then the arrow for x equals 4 is up here. -3 is over, we'll do -1 up here, negative another one here, negative another one here. And there's another point. These points are on my graph of h of x. Then I replace the x in my h of x. Plus x plus 4. I get -3 log base 2 of x plus 4. I know that's a horizontal shift of 4 units. I'm going to get in trouble because that board will fall off when I do the shift here. So I'm going to avoid that. Okay, well, the horizontal shift of 4 units. Here's 4 units. I take each of these points and shift it over 4 units. And I get at least a point here, and a point here. And if I shift this one over 4 units, well, it's going to go a little further. Well, here's my K of X. It's h of x minus 4, which is -3 log base 2 of x minus 4. Well, then finally, I have my m of x. And really, let's look at this thing that I labeled m of x, because really, we've got another name. M of x, we subtracted 4 from the y value. K of x. Okay. Function that we get when we vertically stretch a factor 3 to reflect is -3 log base 2 of x. Place x by x plus 4, we get -3 log base 2 of x plus 4. So we've constructed these two graphs. Now, if we subtract 4 from the y value of k of x, we get -3 log base 2 of x plus 4 minus 4. Now, we don't subtract this 4 from this part. It looks like maybe you could do that, but that's way beyond what we could do. Okay, totally. Yeah. This 4 is trapped inside this log base 2. It's combined with that. Okay, what's this? This is our original function. So this m of x function, labeled here, is really just f of x. Let's think about it now. We start with our function, the basic function, and we try to build up this function. First thing we do is we multiply the log base 2 by -3. Then we replace x by x plus 4. And then here's our m of x. And like we did here, we can identify here that's really just our m of x. That brings us back to where we want to be. So when we do this, we're going to get our f of x function. So we shift every point down 4 units. We're gonna get a little messy. Point goes down 4 units. This point goes down 4 units. This point goes down 4 units. Yeah, this point would if we were doing that to the original function, but it's this point that goes down 4 units. That point is on the arrow next to go away. There's this point has to go down 4 units. And still do the wrong function, we're gonna do this function. Okay, so I hereby declare these 3 red arrows to be invisible. You can't see them anymore. It looks like I did work. I'm not, I saw it. We're gonna skip this graph down 4 units. That point's gonna go down here. This point go down to here. This point will go down to here. This point will go all the way down. Here, and now we can sketch a reasonable curve. Get rid of this arrow. This arrow. We understand now that this is a graph of f of x equals k of x minus 4, which equals then 3 log base 2 of x minus 4 of x plus 4, should have a plus 1 there, minus 4. Okay, well, that's it. Method we've used many times, but you want to break it down carefully. And if I give you transformations, I probably will give you some kind of a transformation of a basic function. It has 3 consecutive transformations. I'll probably also give you one that has only 1 transformation. So you get a fairly easy transformation problem and then fairly challenging. Okay, well, that's it. So talk a little bit about the exam real quickly. It's going to be in the testing center next week. Need to take it by Friday at 5.